Thank you so much. It's great to be here. Thanks a lot for inviting me. I will talk about this paper joint with Nin Sun and Nin Yu. So they are both in Nanjing Audit University. Okay. Some of you have heard bunch of papers that I have written in the past few years on the problem with matching with constraints. But I think that's not familiar to everybody. So let me talk a bit about what this sort of overall question is. Okay, so as everybody in this room probably knows, the matching theory has been applied to many different kind of like problems in practice. So we talked about labor market matching in the morning, maybe matching ex-convicts to jobs and so on. So that kind of application could be done. We have been the researchers have been helping set up school choice mechanisms in major cities in the US for public school choice and so on. When these applications have been like increasingly done, people have realized that many matching problems are subject to certain constraints. Okay, which means that as the kind of familiar standard two-sided matching models have structures such that, you have a bunch of firms, bunch of workers, firms have certain number of positions, fixed number of positions, and so on. But then oftentimes that model is not adequate because there's no clear concept of capacities, number of seats. So instead, certain regulations might tell you, for example, the firm needs to hire at least certain number of people, i.e., floor constraints, okay, or ceiling, which is that the government might tell you that certain firms should not hire more than certain number of workers on top of, even if it is physically possible for the firm to hire workers and so on. Okay. A little bit more generally speaking, so when I say matching is subject to constraints, so I refer to a property of the model such that, the firm needs to follow certain kind of firm can, the set of subset of workers that a firm can hire is not described necessarily as a simple capacity constraint. Okay, so that's a definition I will keep using in this talk. All right, so like I said, the constraints appear in many cases, and there are very many kinds of possible constraints that you might want to think about. So I already mentioned floor constraints. So certain numbers of workers should be hired in the firm. So one possible application or the real life case is coming from the so-called rural hospital problem. So I suppose many of you are familiar with this. So the problem is that in the medical match application of matching theory, for example, if you run the simple Galen-Shapley algorithm, some hospitals, especially in rural hospitals, rural areas, may have hard time filling any position. Okay, so if you look at the practice in the medical profession, oftentimes there are some constraints or regulations trying to promote allocation of doctors into rural areas. Okay, so one possible policy would be to put the floor of saying that for each hospital in this remote rural regions, at least certain number of doctors should be placed, for example. Ceiling could be the sort of mirror image here. So for example, in the Japanese medical match, which I studied in a separate paper, the government has a Gale-Shapley algorithm-based matching program, but because the government is so worried about putting too many people in a certain area, namely Tokyo region, the government puts the ceiling on the total number of doctors who can be placed through the matching algorithm in each region of the country. Okay. So these are another kind of constraints. The constraint doesn't have to have this floor or ceiling form, of course. Like I said, there are many possible ones. So for example, I could imagine a policy which I call always hiring constraints, meaning that in a particular firm, a particular worker should always be hired. Okay? Or never hiring constraints, which means the certain worker can never be hired to a certain firm, possibly because of maybe national security reasons or something like that. So a certain person cannot take a certain kind of job. There should be something in the middle also, and this should be familiar. So in the school choice, well, oftentimes there's a constraint saying that, well, there should be certain balance of the types of students in the student body in any incoming class of the school in terms of socioeconomic classes and so on. So the affirmative action or diversity constraint in schools. Okay. So I could enumerate a lot of these possible constraints, and there are many papers on each of these kind of types of constraints. Some of which have been actually contributed by people in this room. So instead of looking at these constraints separately, today I'd like to step back a little bit and think of a general class of constraints, meaning that roughly speaking, I would just say think of a constraints to mean that the list of all the possible subset of workers who can be hired at any given firm. Okay, so that's arguably a very general class of constraints. And ask the following question. What kind of constraints would allow the algorithm, like Getty-Shapley or market algorithm actually, to work well in a certain sense? Okay. A little bit more specifically, okay. A little bit more specifically before I make sure the slides work. Okay, great. So I will look at the, let me be a little bit more specific. Okay, so I will look at the very familiar model, standard model of job matching, a la Kelso and Crawford. All right, so you have a bunch of firms, bunch of workers. There are some transfer, and people care both about the identity of your partner match, but also the salary and so on. In that model, we know that under a bunch of conditions, most important is the so-called substitute condition. We get existence of a Walrasian equilibrium, which we usually interpret to be a nice solution because it's efficient and so on. We ask the question: what kind of constraints, let's say regulation by the government, will still allow the equilibrium to continue to exist, all right? Of course, the subset of Walrasian equilibrium in this context also corresponds to the stable match. So you can actually compute the stable match by running a version or a generalization of the default acceptance algorithm. So if we think of a government trying to organize a centralized matching market, the motivation is that what kind of constraints the government interested in, let's say, distribution concern, government can still impose certain regulations and still get a nice outcome and run the algorithm nicely. Okay, so that's going to be the sort of question I'd like to ask, but specifically is this one. So what kind of constraints imposed by the government still guarantee the existence of a Walrasian equilibrium? Okay. So instead of asking this question directly, however, like I said, from the previous literature, we know that if the firm preferences exhibit substitutability, then the Walrasian equilibrium exists, all right? And indeed, the later results, such as Good and Sacchetti, say that the substitute is pretty much the necessary and sufficient condition for guaranteeing existence. in a maximal domain sense, right? So instead of asking this question of the existence of a origin equilibrium, I ask, okay, okay, I asked this question. So think of the following question instead. So suppose that firm's revenue function is such that the Kelso-Crawford substitute condition is holds. Now imagine that the government imposes a constraint on that firm, and firm needs to solve the constraint optimization problem. Then the demand function will be computed. Now, what is the condition on the government imposed constraints such that the result of this constraint optimization problem of the firm still continue to exhibit the substitute condition. Okay. So that's a sort of paraphrasing of the question of existence of origin equilibrium. Okay. So that's going to be the main question I will ask. Okay. So that's the main thing, but then after that, I will make sure if that will actually translate to the okay, the computer continue to act problematically. So let me actually close it once and here we go. Okay. Okay. So this is the first question. And the answer turns out to have a very simple form. Okay. So we give a bunch of the cases in which the substitute condition will be preserved under constraints. For example, the ceiling is a very easy one. Ceiling again means that the government imposes the upper bound of the number of workers the firm can hire. Okay, so that it seems to be rather natural that if the government just truncates the number of people who you can hire, then the firm's demand function is still well behaved, and it turns out to be the case. Okay, so ceiling constraints will preserve the substitute. Somewhat more surprisingly, the floor constraint also satisfies satisfies this requirement. I.e., if the government imposes a requirement that the firm needs to hire at least a certain number of people, exogenous given number of people, then the implied behavior of the firm still exhibits substitute. Okay. In addition, the always hiring constraint, i.e., there are a bunch of some subsets of workers who should always be hired, and the never hiring constraints, i.e., certain subsets of workers can never be hired by this particular firm. They keep satisfying the substitute condition, as it turns out. And of course, their combinations will satisfy the substitute condition. And but it turns out that actually they are the only cases also for the substitute condition to be preserved. Okay. So in particular, not the very familiar constraints such as the type-specific upper bound quotas, like affirmative action type constraints, they turn out to actually potentially cause a problem, i.e., even if the firm's revenue function itself exhibits substitutability, if the government imposes affirmative action type constraints, then the implied behavior might actually lead to the failure of the substitute. Yes?
So I'm just trying to make sure I'm understanding. You motivated substitutability as being important for existence. But with floor constraints, we know we might not have existence.
That's a very good question. Actually, in our formulation, floor doesn't actually. We require at least that the constraints of different firms should be consistent, i.e., there should be at least one feasible match where the constraint for each firm is satisfied. But other than that, it turns out that floor constraint is actually not going to lead to non-existence. Which might actually sound, that's a great question because typically floor constraints are the very typical example in which substitute will be violated in the matching problem and leads to the failure of the existence. The reason here is, okay, so you might expect that, and we certainly expected that to be the case. It turns out that the floor constraints type problem is known to cause a problem in matching without transfer typically. I.e., so if let's say let's think of a school choice where a certain school needs to each school needs to have at least 100 people, 100 kids in order to operate. If the number of kids who are even willing to go to the school, certain school, is less than 100, then there's no way to make sure that the matching is individually rational and feasible. Here we are in a different model actually, where there's a transfer. Okay. And we allow for both positive and negative transfer, and unlimited amount actually, possibly. And that means that, using this analogy, so if the government says that a certain firm needs to hire 100 workers, and let's say the firm is so such an unpleasant place to work for, and not many people would work for that firm, the price will adjust, and the salary goes up so much that the workers will find it to be actually individually rational. So that's why my claim is consistent with what you proposed. So basically, importantly, we are looking at a market of matching with flexible salary. Yeah, thanks. That's a good question. Okay, any other question or? Okay, so all right, good. And yeah, okay. So again, so these four cases, types of constraints and their combinations, exhaust the class of all constraints that preserve the substitute condition. So which we refer to as a generalized interval constraints. So interval in the sense that there's a lower bound and upper bound, so it's like an interval. And generalized because in addition we can specify certain particular subset of workers who are never hired or are always hired. So in that sense, it's generalized. Okay. All right. So that's the main result for today. Using that, so we will look at some structure, existence and structure and so on of origin equilibrium. Okay. So it turns out that well, like I said, as long as these constraints are satisfied, the substitute is preserved, then the existence of origin equilibrium is kind of standard. In addition, we can show the lattice structure of the origin equilibrium prices. And perhaps surprisingly, we also get the A version of rural hospital theorem. Okay, so for those of you who are familiar with the hospital theorem, in the matching without transfer, the claim is that under a bunch of conditions, the number of workers matched to in each firm is constant across all the stable matchings. And as far as we know, the results does not quite work in a market like those in the Ikea-Coforth, because you have a continuous prices. So if you could have two origin equilibria where the prices, salary of the workers is exactly like make the worker indifferent between working and not working. In that case, there can be two origin equilibrium where one worker is working. There may be another equilibrium with the same price where that worker is not working. So in that sense, the usual rural hospital theorem doesn't work. But we have a slightly different definition of rural hospitals, and it turns out to work actually. So roughly speaking, the set of set of origin equilibrium allocations have the property that if you change the origin price system from one to another, then the number of workers matched in each hospital will be the same in the set sense actually. The set of number of workers matched with each hospital will be constant across different salary schedules. Okay. And then we talk about the comparative statics when the constraint changes. So as you might expect, if you make the constraint stronger, then in the sense of maybe putting making the floor constraints more strict, then you might expect that that means firms need to hire more workers, so workers should be better off, and firms should be worse off, and so on. So we verify that that type of claims. But again, because we have a set of Y-chain equilibriums, we need to be a bit careful about what the set order is. The answer turns out to be weak set order. Okay. So yes. Okay. Okay. So if you don't have any questions so far, let me actually be a little bit formal. Okay, at least. Okay. So here's the model. So I refer to doctors and hospitals following the sort of matching application, the medical match applications, but we can think of it as firms or workers and so on as well, if you want. So in any case, there's a set of doctors, which I denote by D, and when I write the vector S, that's a vector of salary, one for each doctor. Okay. And importantly, the wage can take any real value, and that turns out to be important, following our discussion earlier with Nick. On the other side of the market, there's a set of hospitals H, okay, and we suppose that there's an outside option, which I denote by H naught, okay. So matching mu, which I denote by mu, specifies which doctor works for which hospital, if any. Of course, the doctor could take the outside option. The outcome, however, of this market is not just described by matching, because, like I said already, informally, we have a model with flexible transfer salaries. So the allocation, which is the outcome of this model, is a pair of a matching and the salary schedule, right? Mu comma S, all right. And I have a restriction that the salary for Dr. D should be exactly 0 if, well, the doctor is matched with the outside option. So that's the additional restriction for this to be qualified as the outcome of this market. All right. Okay, so this is kind of preliminary, I guess. So let me describe the constraint in a somewhat formal manner now. Okay. So like I said, I don't want to sort of exclude certain constraints a priori. So in a most general form that I can think of, the constraint is described by this object, FH. So script FH, so H is a hospital, and we are thinking of a constraint given for each hospital separately. Okay. Which, by the way, it does exclude certain applications, like the Japanese medical match example that I mentioned, because then the constraints are actually imposed over sets of jointly or subsets of hospitals. With that caveat, the general notion of constraints is simply a subset of a power set of D, meaning this collection of feasibility. This collection includes all possible subsets of doctors, which is deemed to be feasible at hospital H. Okay. Of course, if we only have a capacity constraints, upper bound constraints, then this feasibility collection is made up of all subsets of doctors whose cardinality is less than or equal to some number. But we are not imposing that restriction on the constraints here. Okay. So we actually allow for some constraints to come from the firm's own concern, which I denote by F naught. But in addition, we are thinking of a government imposing some restriction, the constraints, which I denote by F superscript G. Okay, the entire constraint is given by the intersection of the intrinsic constraints, self-imposed constraints, and the government-imposed constraints. Okay. So if let's say the farm has a natural capacity constraints that the farm can have space enough only for 50 people, then this F naught describes this kind of constraints. But if the government in addition says the farm needs to hire a certain number of minority workers, then this is described by F superscript G. Okay. So that's a constraint. Yes.
Possible to incorporate in the setting also restrictions in the salaries? Because you could imagine that in a cycle of transfers, you could also regulate not only who gets hired, but also what salaries they.
That's a very nice question. Yeah, so you are definitely right. So one could imagine having salary cap, salary floor, and so on. In this paper, we do not actually, we do not allow that. And when I said actually that's as general as possible, I'm a bit maybe I'm saying a little bit not clear on that actually. Thank you. Yeah. So in particular, we are not allowing for things like budget constraints where the firm can pay at most a certain number of US dollars. Yeah, that's right. Yeah, thanks. That's an important clarification on the class of constraints, actually. Yeah. Okay. All right. So I talk about feasibility of matching. So I naturally I say that matching is feasible if, well, for each hospital, the set of workers who are matched in that matching is feasible according to the constraint associated with hospital H. All right. And coming back to the earlier conversation with Nick, at least we assume that this set of feasibility collections, the constraints are compatible with each other in the sense that at least there exists one feasible matching. Otherwise, well, it's probably not that interesting. Okay. All right. So is everything clear so far? I mean, with help from Nick and Laura. Yeah, great. Okay. Yeah, thanks a lot. Okay. So I have not actually described the utility yet, so let me do it now. Okay. So this is not totally the main part of the paper, but we are a bit more general than many existing papers. So like I said, we have continuous transfer, but we are not necessarily imposing quasi linearity. So when I write U sub D comma H of S, so this is the Dr. D's utility when matched with hospital H at salary S. Okay. So we impose the usual restrictions such as, well, the utility should be strictly increasing in money and also continuous. Okay. And also we want the money to be important enough that, well, to impose this condition, which it says that take any pair of hospital H and H prime, and then compare the utility for this particular doctor when matched with H and H prime. Then put any salary S, there exists large enough S prime, double prime that D would rather be matched with H prime. And there's also a small enough salary such that D would rather be matched with H. Okay, so the money is important enough. Of course, quasi linearity implies this.
Is S allowed to be negative?
Yeah. And that's important, thank you, yeah. Okay, yeah, exists S, yeah, so everything is in R, yeah. Great. All right. How about hospitals? Well, it turns out that we actually need to impose quasi-linearity for the hospitals, actually. Namely, so this R sub H of A is revenue for hospital H when matched with a subset of doctors A. Okay, and profit is just quasi-linear. So the revenue from hiring a set of workers A minus the salaries being paid. Okay, and that will induce naturally the demand correspondence, which I denote by X. Okay, here the argument of the demand correspondence is not only the salary schedule, but also the set of constraints. Okay, so the firm needs to optimize within the feasible set as specified by the feasibility equation F. Okay. So if there's no government imposed constraints, then that's the usual demand correspondence. I refer to it as an innate demand correspondence. Yes.
If you're going to impose substitutability, why is quasi-linearity important for the hospitals?
So you are saying that you could define some kind of substitutes when the underlying utility function does not have to be quasi-linear. So that's very short answer is that our analysis doesn't work, and in particular, for us, it actually turns out to be very important for us to exclude some kind of income effect, actually. Let me try to explain it now a little bit, but then come back to it when I talk about the theorem. So like I said, we have this characterization of the classes of constraints that preserve the substitute condition. And the sufficiency of our class for preserving substitute condition is based on the following observation. So suppose that, so remember that so think of a simple case where we only have floor constraints and ceiling constraints, i.e. the minimum number and maximum number to be higher, in addition to, of course, the firm's own concern. Let's imagine that what we do is the induced demand, if you have, let's say, so imagine that the firm is subject to floor constraints. Then the induced demand at any given salary profile can be described as if it is actually the innate demand correspondence for different salary schedule from the original salary schedule. Sorry, so this is the this is a constrained demand, and so what I'm trying to say is that you can actually show that. So let's say this government imposed constraint is just a floor constraints, okay, meaning a minimum number of hiring. It behaves as if it is a demand without constraints, but when faced with a different salary schedule, and the salary schedule is such that okay, so salary schedule has this form. This hypothetical salary schedule S prime is the original salary plus some epsilon, some number, a real number, plus the vector, vector 1, which is like entry vector with entry 1 for every worker, meaning that the firm behave as if they are facing the uniformly higher price by the same amount. Because if you have a floor constraint, if under the given price schedule, let's say the floor is not is violated. Oh, I see. Sorry, I said the opposite actually. Then the firm, you can show that the firm is actually just going to increase the total number of hiring, but by imagining that the prices for all workers are lowered by the same amount. So the relative, so in a sense, relatively which workers are more preferred and so on does not change because the prices are going to be lowered by the same amount, and hence then you basically so that you hit the floor. But when we do it, then we actually use a lot of properties from quasi-linearity, basically. So, like I said, unfortunately, that's not the full explanation. I apologize. But this intuition that if you have a floor to satisfy, then you can you can sort of imagine that the prices are low for all workers and hence increase the number of hiring, but you should not sort of trade off who to hire and so on differently. But this intuition does not hold if you have an income effect, basically. Sorry, that's the best I can give right now. Okay. Okay, any other comments or questions so far? All right, good. Okay, coming back. So we have described the. Okay, now substitute condition. So this should be familiar to many of you. So let me be a bit quick. So substitute says that if the salary schedule goes up, then for the firm that I somehow mistakenly you have I have 3 minutes. Okay, yeah, so somehow my timing was wrong. Okay, good. Okay, so substitute says that, well, if the prices of some workers goes up, then the firm can keep hiring the workers whose prices did not go up. And the condition for the government imposed constraints to preserve the substitute condition means that, well, if the innate correspondence satisfies the substitute, then after imposing government constraints, the demand correspondence still satisfies the same condition. And this should be true for all, importantly, for all substitute variations. So that's for all parties kind of like important for getting the result. Okay, so think of a simple case where there's no doctor who is always hired or never hired. Okay, so this is a subclass of problem we look at. And so I already mentioned what characterizes the constraint that preserves the substitute condition. It turns out to be what I call interval constraints, meaning that there exists some number floor and ceiling, and the feasible set is described simply by all subset of workers whose number is between the floor and the ceiling. And for this case, the theorem is that the class of all constraints that preserve the substitute condition is described by this interval constraints. Okay. All right. So actually, answering the Alex's question, so I explained this part, and this is pretty much the main part of the sufficiency condition. Like I said, if you have a floor or ceiling, then the demand of the constrained demand will behave as if it's unconstrained demand, possibly with modified prices. So to the extent that the original unconstrained demand follows the satisfy the substitute condition, the constrained demand continues to satisfy the substitute condition. Although it's a little bit more subtle because this S prime could also depend on what S is and so on. All right. The necessity we will look at a particular subclass of substitute condition, and basically it's a sort of glorified version of the finite counterexamples. All right. Okay. And with my miscalculation of the times, let me skip.
You have 5 more minutes.
Say again?
I think I made a mistake.
Okay. Oh, I have 5 more minutes. Thank you. Great. Okay, thanks. Okay, good. Okay, good. Yeah, it's always good to get more time than expected. Great, thanks. Okay, great. So this interval constraint is a specific case in which there are no people who are always hired or never hired. What if we do not impose that constraint? Then we get a generalized interval constraints, like I said. All right. And then, we can show the existence of a competitive equilibrium. Basically, as long as we have these constraints, but they exhibit the constraint demand continues to have substitute, the Bayesian equilibrium exists. Oh, the part which is not totally obvious is that actually we started out without imposing quasi-linearity for the worker side, but then we actually need a little bit condition saying that the money is important enough, which we call the bounded compensability. With that assumption, we get the existence. Okay, so I already said that we have a lattice structure of the set of equilibria but let me focus on something that may sound even more interesting. Okay, rural hospital theorem. So I already said that usual, yes?
So for existence, do you do like Kesokrofa?
Basically, right. So basically, yes. So we have, right. Yeah, basically, we follow the Kelso-Crawford proof, basically, because yes, the answer is yes. So we discretize the market and then take the limit. So for the discrete market, we can show the constructively show the existence. And with the enough assumption on the worker preferences, which is not exactly creates a linearity, but we have enough of the continuity and so on, we can show the limit is also, limit is actually a valid equilibrium in the limit. Yeah. Okay, rural hospital theorem. So like I said, the following is not true. Take any two variable equilibrium, the set of people hired are the same. That's not going to be true because there are a lot of indifferences. What we can say, however, is the following. So take one variable equilibrium, mu and s, and take another equilibrium prices s prime. Then there exists a matching mu prime such that, well, mu prime and s prime is a equilibrium. And between mu and mu prime, the number of workers hired are the same, as well as the set of workers who are not hired. So basically, if you compare the set of all the equilibrium matchings associated with given variable equilibrium prices, then as such a set, they have the same the conclusion of the Euler-Hochschild theorem across different variable equilibrium prices. Right. Okay. Okay. So finally, comparative statics. So like I said, we are looking at a set of variable equilibria. So we should be a bit careful about the ordering. So we use a well-known concept of weak set order, meaning if you want to compare two sets of two sets, and one set is higher than the other set, if take any element from the lower set, first set, there exists something element from the other set that such that the latter is higher than the former, and vice versa. And that so this, according to this notion of order, we get this result, which says the comparative statics. So if you lower the ceiling, I mean make the ceiling constraint stronger, then variable equilibrium prices go down in terms of this weak set order. If you put into the floor, then that will raise up variable equilibrium prices. Okay, so the prices move in a sort of like a reasonable way. And associatedly, if the prices are higher, then workers are better off and firms are worse off, basically. Okay, so that's going to be the comparative statics. But importantly, this conclusion is not going to be necessarily true if we were to use a maybe more familiar strong set order, which people often use. All right. So great.
Counterexample with strong set order?
Yes. So I can come up with it off the top of my head, but I believe that I have one. I have one somewhere. Yeah. Sorry. Okay. Yeah. All right. Okay. Yeah. So okay. So here's the so the last thing. So we are currently working on the similar question, but now the government we are thinking of a transfer policy. So now instead of the government mandating the set of workers who can be hired in the given firm, think of a worker. So the government giving a tax or subsidy, okay, depending on who are hired, and we have a preliminary. Oops. Is saying that I should finish. We have a results characterizing the types of transfer policies that the government can impose in such a way to preserve the substitute condition. But that's for another talk, I think. And okay, so sorry for I think I missed the target, so I should finish now. Thank you.
We do have a couple of minutes for questions.
the last point about tax and subsidies. I mean, a priori, could you compare the instruments like quantities, floor and ceiling, and
yes.
like in the standard Weitzman model?
So how you compare this kind of constraint band?
Which one is preferable, under which?
Yeah. Okay. Yeah. So we know just a little bit about it. So because we have not done too much of it for this second project, but one thing I can say is the following. So in our framework, we can show the following. So suppose that we are given this constraint in the sense I explained in today's talk, and then compute the computer equilibrium. Variation equilibrium under constraint. Now, there exists a transfer policy such that under that transfer policy, the this same equilibrium is going to be realized. So, in the sense, there's a sense in which any policy based on this constraint can be replicated by the tax and transfer policy. So that we know, but that's the only thing we know so far. But in some, if we think of some kind of, so we have not, we like to study more about when actually the tax subsidy policy is more preferable or vice versa. But our current framework does not allow us to ask that question. Basically, it's going to be so left for another project.
Thank the speaker again.
Thank you.